Hi guys, and welcome back to the ACE Academy. In this video, we'll be looking at parallel circuits. On your screen, you can see that I have sketched a simple parallel circuit for us to investigate to figure out the relationship between current, voltage, and resistance in a parallel circuit. This circuit is made up of two resistors connected in parallel with a battery. We have voltmeters measuring the voltage across each component. We have ammeters measuring the current the current that flows through each component. In order to grasp this type of circuit correctly, we are of course going to need a bit of theory. So what I have done is listed two main bits of theory that you will need in order to attempt a parallel circuit. The first one is perhaps the most important one, and that is the fact that voltage across parallel branches are equal. Now, when I say that the voltage across parallel branches are equal, I want us to look at this example and see the relationship between the source voltage and the voltage across each component. In this circuit, the battery has a total voltage of 12 volts. That means that the battery supplies 12 volts to this circuit. Looking at the branch that contains resistor R1, we can see that the voltage across this resistor is 12 volts. If we look at the branch that contains the resistor R2, we can see that the voltage across this resistor is also 12 volts. This means that the total voltage Vt is equal to the voltage across R1, which is also equal to the voltage across R2. So simply put, if this was my parallel connection only, the voltage across R1 would be equal to the voltage across R2. That is very, very important. It's going to allow us to approach this type of circuit with knowledge that we can apply. The second important bit of theory is that current is divided in this type of circuit. This type of circuit is what we call a current divider. Now let's refer back to our series circuit theory. For series circuit, we knew that voltage is divided across each component, whereas in parallel circuits, voltage is equal across parallel branches. For a parallel circuit, the current will divide through the branches in the circuit. Let's analyze this. This circuit has a total current of 3.6 amperes. This means that as current leaves the battery, we will have 3.6 amperes of current flowing through the circuit. But once it approaches this node right here, this junction rather, a certain amount of current will break off and travel through this branch, and a certain amount of current, the remainder of the current, will break off and travel through that branch. It will travel through the components, it will travel through the branches, and eventually it will reconnect and form the total current again. Let's look at this in detail. I have 3.6 amperes of current being supplied by the battery. It follows the path of the wire until it reaches a junction where the current splits. Looking at the first branch, the branch that contains resistor R1, I would have 2.4 amperes of current that flows through it. Looking at the second branch that contains resistor R2, I will have 1.2 amperes of current flowing through it. Once it reconnects at this node, the current will recombine. This means that A1 plus A2 is equal to A3. So in short, the total current in a parallel circuit divides at a parallel connection. Let's look at it, let's investigate it a bit more so you can grasp it more clearly. 2.4 amperes is the current I have running through the first branch. When I add that to the current running through the second branch, which is 1.2 amperes, I would get 3.6 amperes. In this way, current is conserved through the circuit. In order for us to calculate the amount of current that travels in each branch, we can simply take the voltage across that branch divided by the total resistance of the branch itself. So in order for me to calculate the current running through the first branch containing resistor R1, I would simply take the voltage across resistor R1 divided by the resistance of resistor R1, which is 12 divided by 5, and I would obtain 2.4 amperes. In order for me to calculate the current flowing through resistor R2, I would take the voltage across resistor R2 divided by the resistance of resistor R2, and I would obtain the current flowing through resistor R2. So that will be 12 divided by 10, which is 1.2 amperes. And simply, when it reaches this junction right here, it recombines again and is supplied directly back to the battery. That's just a bit of important theory that you guys need to grasp. We are now going to go ahead and do an example together just to reinforce this bit of theory. On your screen, you can see that I have created a new parallel circuit. This circuit is made up of two resistors connected in parallel to a battery. Let's look at the information that has been given to us for this parallel circuit. We have the total current in this parallel circuit, and we have the resistance of all the resistors in the circuit itself. We do not know the source voltage, we do not know the current through the branches, we don't know the voltage across each resistor. We have total current. There is no way for us to work out total voltage just yet. There's no direct method. So what we can do instead is work out the total resistance. How do we calculate total resistance for a parallel circuit? We simply use the formula 1 over RT parallel is equal to 1 over R1 plus 1 over R2. If I substitute in my values for R1 and R2, I will get 1 over RT parallel is equal to 1 over 3 plus 1 over 6. If I simplify and expand, I would obtain 1 over RT parallel is equal to 3 over 6. I would now invert this fraction in order to obtain RT parallel. So therefore, RT parallel is equal to 6 over 3, which is equal to 2 ohms. Now that I have the values for total current and I have calculated the value for total resistance, I am now able to calculate the total voltage in the circuit. This can be done simply by using Ohm's law, where total voltage is equal to total current times total resistance. Substituting in my values, I would obtain 12 times 2. Simplifying, I would obtain a total voltage of 24 volts. I now know that my source voltage is 24 volts. The next question asks us to find the reading on voltmeter V1 and V2. Let's look at this and apply some theory. We can see that V1 and V2 are in parallel to one another. We can also see that this connection is also in parallel to the battery. So V1 and V2 are in parallel to V3. So simply put, applying our theory, the fact that we know that the voltages across parallel branches are equal, we would be able to see that V1 is equal to V2, which is equal to V3, and we know V3 is equal to 24 volts. So V1 is equal to 24 volts and V2 is equal to 24 volts. The next question asks us to calculate the current flowing through ammeter A1. We can do this by using the voltage in this branch and dividing it by the resistance of the branch itself. Why can we do that? Because of Ohm's law. Ohm's law tells us that I, or current, is equal to voltage divided by resistance. So that means that 24 volts divided by 3 ohms should give us a current value of 8 amperes. In order for us to calculate the current on A2, we have two different methods. The first method that we can use is the same as the method we used in the previous question. We can take the voltage across the resistor, which is 24 volts, and divide it by the resistance of this branch, which is 6 ohms, and we would obtain a current value of 4 amperes. The second method that we can use to obtain this value is quite simply using the current divider bit of theory that we have learned. We know that the total current in this circuit is equal to the sum of the currents in the branches. So A3 is equal to A1 plus A2. Simplifying and manipulating, we can find that A2 is equal to A3 minus A1. Substituting in my values, we would find that A2 is in fact equal to 12 amperes minus 8 amperes, which is equal to 4 amperes. We use two different methods to obtain the exact same answer. This bit of circuit theory is a bit complicated, but with enough practice, I'm sure that you would be able to ace it like you always do. That's it for me, guys. All the best, and I will see you in the next one.